Chem 212, Exam 2 Material, Part 3. Alkenes, Structure and Reactivity. An alkene is a hydrocarbon with a carbon-carbon double bond. They're also known as olefins, but the name alkene is much better. It includes many naturally occurring materials, such as flavors, fragrances, and vitamins. Important industrial products. We can take the reaction of cracking of natural gas. Natural gas is when you have alkene chains between 1 and 4 carbons, and gasoline is when you have 4 to 8 carbons. So when we take a look at this reaction here, this is the cracking industrial method of cracking. This is a reaction you definitely want to know. We can have anywhere between 1 and 8 carbons, and so this is kind of a generic way to write this. So we're looking at 850 to 900 degrees C and steam, and what this does is it breaks down the alkane into hydrogen, methane, and these different alkenes. We have ethene, propene, and 1-butene. So knowing the industrial reaction of cracking natural gas and gasoline is something you do need to know for this class, and what products are formed. Degrees of unsaturation. Now that we're starting to talk about alkenes would have a carbon-carbon double bond, and we've already talked about cycloalkanes, now's a really good time to bring up degrees of unsaturation, or DOU. When we're looking at degrees of unsaturation, we're actually looking for the number of rings or multiple bonds in a compound. For each ring or multiple bond, it replaces 2 hydrogens. How you figure out degrees of unsaturation is you add up the carbons first. Then you calculate 2n plus 2 for the number of hydrogens if it were saturated. I would like you to recall that the formula for an alkane was CnH2n plus 2, and that's when it was saturated. This is the formula for something saturated, and that's where this piece here comes from. After you calculate 2n plus 2 for the number of hydrogens, you add up the number of hydrogens in the formula you're looking at, and then you find the difference. Divide by 2, this is the degrees of unsaturation. How you handle it when you have an organic compound that has halogen, oxygen, and nitrogen, you add halogens to the number of hydrogens you had in your formula. You completely ignore oxygen. It doesn't really play any part in the degrees of unsaturation. And you subtract nitrogens from hydrogens in your formula. Remember, the CnH2n plus 2 to find the saturation is your key point, and you compare that to the formula you're looking at. Calculate the degrees of unsaturation in the following. For the first 3, you can go ahead and compare the formula to CnH2n plus 2. For 4 through 6, you can do it a couple of ways. You can go ahead and find the molecular formula and do it the same way you did 1 through 3, but I want to give you a hint. Every time you have a double bond, you have 1 degree of unsaturation, and every time you have a ring, you have 1 degree of unsaturation, and some molecules can have more than 1 degree of unsaturation. So go ahead and pause the video, fill out the number of degrees of unsaturation, and come back and see how you did. For this first one, Cn, I have 7 carbons, so that'd be 7 times 2 is 14, plus 2 is 16. So 16 would be if I had 7 carbons and it was saturated. I only have 12 carbons. The difference between 16 minus 12 is 4. I take that 4 and I have to divide it by 2, and I get 2 degrees of unsaturation. C6H8, 6 times 2 is 12, plus 2 is 14. If it were saturated with 6 carbons, I'd have 14 hydrogens. I have 8. The difference, 14 minus 8 is 6. Divide that by 2, 3 degrees unsaturation. We have 3 carbons. 3 times 2 is 6, plus 2 is 8. I only have 4 carbons. The difference is 4. 4 divided by 2 is 2. All right, 4 through 6, I didn't do it this way using the molecular formula. I just counted how many multiple bonds I had. What I didn't mention before is if you have a triple bond, you have 2 degrees of unsaturation, and I did mention if you have a double bond, you have 1. So let's count. I have 2 double bonds. That means 2 degrees of unsaturation. In this case, I have a ring, And one ring is 1 degree of unsaturation, but I also have a double bond. That would be 2 degrees of unsaturation. 1 for the ring, 1 for the double bond. In this case, oxygens don't play a part at all, so that doesn't matter. I do have a double bond here. Nothing else unusual going on. Actually, I only have 1 double bond, so I have 1 degree of unsaturation. All right, I have a bonus question because I didn't do anything with nitrogen in these examples, and you can get some more examples from your textbook, but let's do this bonus problem. I have CH3, CH2, NH2. So let's take a look at this. If I did CnH2n plus 2, I have 2 carbons, so 2 times 2 is 4, plus 2 is 6, so I should have 6 hydrogens. Well, I have 3, 4, 5, 6, 7. But did you remember the rule said if you have nitrogen, you have to take away one of the hydrogens? I have no degrees of unsaturation in this case. Naming alkenes. Name the longest chain which contains the entire double bond, the beginning carbon and the end carbon. Number the carbon atoms in the main chain that gives the double bond the lowest possible number from whatever end it's closer to. So now the double bond has priority over the substituents we've seen so far. Identify the substituents in the chain and number them. And alkenes have an ENE ending. Write the full name as one word. Here is an example of 1-propene. Now I went ahead and gave you the structure of the name right off the bat because one of the things I want to make sure you get good at is it doesn't matter if the double bond's on the left-hand side or the right-hand side. This is carbon 1. Wherever the carbon is that starts the double bond, whatever end it's near, that gets to be carbon 1. Now when we give it its name, this one here is telling me where the double bond is. We understand that it ends on number 2, so we never include the number 2 in its name. It's understood it's starting on 1 and ending at 2. So let's take a look at these examples. I have 2 carbons here, double bonded. There's nothing else coming off of it. That would be ethene. And I mentioned earlier that your textbook loves calling this ethylene, which is its common name. You need to be familiar with both. We're looking at the IUPAC name ethene at this point. Okay, on this one, my longest continuous chain, which contains the double bond. I don't have any substituents. It's starting on carbon number 1. There's 3 carbons total. Propene. Here we have the longest chain, and we have a substituent. This is a methyl group. The double bond, the end that it's near is here. That's carbon 1, so that means I have a 2-methyl group. The name of number 3 is 2-methylpropene. On number 4, don't forget that you have to include the entire multiple bonds. So the longest chain, which contains, in this case, 2 double bonds, is here. So I haven't shown you what to do when you have 2 multiple bonds. But let's take a look at the numbering system first. Notice that if I started on this end, I would have a double bond starting on carbon number 1. And if I started on this end, I also have a double bond starting on carbon number 1. But what makes the difference is this methyl group right here. It needs to get the lowest number because the double bonds are tied going from left to right and right to left. So I have to give this substituent the lowest number. So that means this gets to be carbon 1. My methyl group is on carbon number 2. Oops, that's not number 2 there. Let's put it here at 2. And my other bond starting on carbon number 3. How you name something that has 2 multiple bonds? Well, we know we have a 2-methyl group. We talked about that already. I have a multiple bond starting on 1 and 3. That's where this 1 and 3 is coming from. Take a look at what they do to the alkene name. They split it up. What I really like about OCHEM is when they put a multiplier, they put it exactly in front of what they mean more than one of. So what they're going to do is we have 4 carbons, so that would be butene, but because we have 2 of them, they change this to buta. The di means 2. What does it mean 2 of? 2 double bonds. Literally, the multiplier is exactly in front of what they're talking about. So butadiene means I have 4 carbons with 2 double bonds. Where are they? On carbon 1 and 3. Additionally, I have a 2-methyl group coming off of this 1,3-butadiene. Many alkenes are known by their common names. This first one here, ethene, is known as ethylene. So we've seen that in your book, and your book loves using that one. Propene is also known as propylene. 2-methylpropene is also known as isobutylene. This 2-carbon thing, 2-methyl-1,3-butadiene, is known as isoprene. And 1,3-pentadiene, it is piperylene. So which ones do I need you to know? Go ahead and know the first two, ethylene and propylene. Know those common names. Your textbook uses them a lot. For everything else on this chart, I want you to go ahead and know their systematic name or their IUPAC name. But additionally, underneath this table, we have what's known as a methylene group. I do need you to know that. A methylene group is either a CH2 group or a CH2 group with a double bond coming off of it. That's a methylene group. So a CH2 group, either single bonded on both sides or double bonded on one side, is known as a methylene group. Methylene is kind of an interesting way because it has a YL in it and an ENE. It doesn't have to have a double bond. It can have single bonds. So keep both of, make sure you know both of those. This is a vinyl group and an allyl group. We'll be seeing these quite a few times throughout the year. A vinyl group is when we have a carbon that is part of a carbon-carbon double bond. This is our vinyl group here. An allyl group is the carbon one away from the carbon-carbon double bond. This is the allylic position. So sometimes we'll say something happens at the vinyl position. That would be the carbon part of the carbon-carbon double bond. When it happens at the allylic position, it's one away from the carbon-carbon double bond. So these are 3 more groups you need to know. On this page, to summarize, you need to know all systematic names. You need to know the common names of ethylene and propylene, and you also need to know CH2, both in single bond form or double bond as a methylene, vinyl, and allyl. For this slide, I want you to go ahead and give me the IUPAC name for each of the following. Go ahead and pause the video, come on back, and we'll see how you did. All right. We have octatriene. We have 3 double bonds in a parent chain of 8, and they live on carbons 2, 4, and 6. Make sure when you have numbers, you separate the numbers with commas, and a number and a letter, you separate it with a dash. This one, our longest continuous chain, is right here. And let's take a look. 1, 2, 3, my double bond from left to right. 1, 2, 3, from this direction, it's also 3. So what breaks the tie is my methyl needs to have the lowest number. So the numbering system goes in this direction. This would be carbon number 1, and my methyl's on carbon number 2. 2-methyl-3-hexene. On this one, here's my longest continuous chain, which contains all those multiple bonds. It's 8 carbons. I have 2 multiple bonds. That's where the di comes in, diene. Where do they live? Well, let's take a look. The multiple bonds have priority in the numbering system. So going from this top part here, from basically left to right, I have a double bond starting on 2. And on this one, the double bond doesn't start until 3. Remember, it's the double bonds that have priority. It's the last name in the compound that gives it priority. So the numbering system has to go in this direction. So this would be carbon number 1, carbon number 2. No, that's not carbon number 2. Carbon number 2. I was skipping there. Carbon number 3, carbon number 4, and so on. So I see a methyl group on 4, 5, 6, 7, and my double bonds are on 2 and 5. On this one, I had to make sure that my longest continuous chain contained the double bond, but it also goes up like this. Did you guys catch this one? I bent this one quite a bit. It's the longest continuous chain which contains the double bond, regardless if it bends and twists. So I have a methyl group here, here, and here, and the double bond has priority on the chain, so this would be carbon number 1, and that's where I have 3, 4, 4, trimethyl 1-pentene. On this one here, longest continuous chain, which contains the double bond, 1, 2, 3, 1, 2, 3. Well, The double bond's tied either direction, so what breaks the tie? The bromo needs the smallest number. The numbering system goes in this direction. This would be carbon number 1, and bromo's on carbon number 3. 3 bromo, 3 hexene. Longest continuous chain, which contains the entire double bond. Here we go. I have this coming off. The priority goes to the double bond. It gives it its last name. This is carbon number 1. It goes in this direction. So I have my methyl group on number 3. 3-methyl-1-pentene. Now this one's just bent. Really doesn't mean anything. I'm showing that 120-degree bonding all around that carbon-carbon double bond, but that doesn't change anything. And I happen to have an ethyl group this time. And this gets to be carbon number 1 because that's where the double bond starts. 2-ethyl-1-pentene. How'd you do? So on these examples, not only do I have an alkene, but I have cycloalkanes. Remember, it's the carbon-carbon double bond that gets priority. And don't forget to use the word cyclo in there. So this will be a fun exercise for you to practice both your cyclo naming along with alkenes. Priority goes to the alkene. So let's go ahead and pause the video, try these, come on back and see some of these names. What happens on these is the double bond gets priority. So this would be carbon number 1 because not only does it have a double bond but something branching off the double bond. So this has to be carbon number 1 and it has to go in this direction because the other side of the double bond has to be carbon number 2. So if you happen to have a double bond and something is coming off of the same carbon on a ring, make that carbon number 1 and be sure to make the other side of the double bond carbon number 2. This means I have a 1,5-dimethyl cyclohexene. My methyls are coming off of 1 and 5. So why didn't I tell the reader in the name where the double bond was? That's because the number 1 and 5, where the methyls are relative to where the double bond was, and I don't give it a number because I know where it is. I would draw, if I were to go backwards, I would draw a cyclohexene, and on carbon number 1, either left or right of this is where I'd put the first methyl, and then I'd come around just like I did here. Letter B, I have to start at one end of the double bond, and there's so many places I can start here, so let's just go ahead and start here. If I start this as carbon number 1, the other side must be carbon number 2, and once you choose a direction, you have to maintain the direction for the whole molecule, so my next double bond is starting on 4, ends on 5. 1,4-cyclohexadiene. Letter C is similar to letter A because I have a double bond and something coming off of it. This has to be carbon number 1, and the other side of it going in this direction has to be carbon 2. So that means this methyl is coming off of, here's carbon 1, 2, 3, 4, 5. And again, it's like we had in the example of letter A. I don't tell the reader the name where the double bond is. It's understood because of the reference of 1 and 5 dimethyl that it is right here. Letter D, this would be carbon number 1. This would be carbon number 2. So my methyl is also on carbon number 1, 1-methyl-cyclohexene. My carbon-carbon double bond has priority, and if I start here and go in this direction, that would give my CH3s the lowest number. Remember, I can't, when I number my carbon, it has to be on one end, and the next number has to be where the double bond ends. So I have to go in this direction here. This would be carbon 1, 2, 3, 4. This would be carbon number 4. I have 2 methyls on carbon number 4 of a cycloheptene. 4,4-dimethyl cycloheptene. Double bond finishes here. This is the closest direction. I want to go in this direction. This is carbon number 1, 2, 3. This is carbon number 3. And this group here is one we haven't seen for a while, but that happens to be an isopropyl. What's really happening is I have a CH3 coming off of this carbon. Actually, I have 2 of them. So let me draw the other one here, CH3. Let me scratch this out here for a second. Now do you recognize this as being an isopropyl? 3-isopropyl cyclopentene. Draw the condensed structural formula and the line Structure for the ring is okay, like we did on the previous slide, for each of the following. Go ahead and draw your structures, come on back, and check your work. Pentadiene, notice this does not have the word cyclo. I know we've been doing a lot of rings. This is not in a ring. It would be 5 carbons in a row. This di is telling me I have 2 double bonds. The 1 and the 4 tell me where they live. Additionally, off of my 1,4-pentadiene, I have a methyl coming off of carbon number 2. So the way I drew this, this would be carbon number 1, 2, 3, 4, 5. 1,3-cyclopentadiene. So I have cyclopenta. That means I have 5 carbons in a ring. This di means I have 2 double bonds. Where do they live? 1 and 3. So once I draw my cyclopent, I can start my double bond wherever I want. Now this would be carbon number 1. I'd actually drew this one backwards the way I'm doing this. So that's carbon number 1, number 2, and this is carbon number 3. In this case, I'm drawing it going in the counterclockwise direction. 3-ethyl-1-hexene. I have 1, 2 carbons, 3, 4, 5, 6. The reason why this is a hexene is because the longest continuous chain must contain the whole double bond. I have 1, 2, 3, 4, 5, 6, 7. This is a longer chain, but it does not contain the complete double bond. So this is a good example to work both ways to get some good practice out of it. 3,6-diethyl-1,4-cyclohexadiene. You would start with the cyclohexa. You have 2 double bonds on 1 and 4, so we have 1. This is carbon number 2. I'm going to go in this direction. Carbon 2, 3. This is carbon number 4 when I go in this direction. And coming off carbon number 3, so this is carbon number 3, I have an ethyl group, and also off of 6, I have an ethyl group. Be sure to check that when you have ethyls that the CH2 is what's attached to the chain, and it's only the terminal carbon that has 3 hydrogens. Okay, here's an example. We have heptene, and I have 7 carbons in a row. My double bond is starting. I only have 1 double bond this time, carbon number 2. So in this structure, I have it going in this direction, and this is my propyl group coming off carbon number 4. Just like we talked about with the ethyl groups, make sure that any carbons that are part of the chain are those methylene groups, CH2 groups. Let's use the word we just learned, methylene. And the very last one has a CH3 because it's the terminal carbon. Draw the structures for the following. On this one, when I give you the answers, I actually did a lot of the structures with line structures. So you might want to go ahead and practice line structures on this if you want to compare them to mine. I did a lot of line structures. Go ahead and pause the video and come on back and see how you did. So I wanted to give you more practice plus have you see some line structures and see how they compare. Diene means I have 2 double bonds on a parent chain of 5. There's no cyclo, so there's no ring. They live on 1 and 4. So I have 1, 2, 3, 4, 2-methyl 1,4-pentadiene. So here's some information I found online. I wanted to look up some additional stuff. I found this link here, and again, the link won't use in the video on YouTube that you're watching. The link will work when you look at my instructor PowerPoint videos I have posted online. The Khan Academy link to how to make alkene compounds. Leah Fish, she does a really good job of doing a whole bunch of tutorials for organic chemistry. I highly recommend going to her website. This is a link to naming alkenes, nomenclature tutorial for double bond organic compounds. I also found isomers, stereoisomers, geometric isomers, cis and trans isomer guides. This is something you're ready for now. The E and the Z will be at the end of these slides. And I just noticed something. That cis is a capital I. It's supposed to be lowercase. So sorry about that. I got a capital I there. It should be C lowercase is. And then I found this what I liked them kind of comparing what is a substitution in an alkene. When they say monosubstituted, that means where you have our carbon-carbon double bond, there's only one R group. These are all examples of disubstituted, In this case, we have our hydrogens on the same side of the double bond, so this would be cis, and we have our hydrogens diagonal, this is trans, and this one just happens to have both hydrogens on one end. Here's an example of tri-substituted and tetra-substituted, and I liked how this described the different types of substitutions for you and gave you some nice examples. Electronic structure of alkenes. Carbon atoms in a double bond are sp2 hybridized. We have 3 equivalent orbitals, 180 degrees separation in the plane. The geometry is trigonoplanar. With alkanes, there is free rotation around a single bond. That is not true with alkenes. The geometry is fixed with the carbon-carbon double bond. Rotation of pi bond is prohibited. We cannot have this happen. It would actually break the double bond. So we do not have free rotation around an alkene carbon-carbon double bond. Cis-trans isomers in alkenes. The presence of a carbon-carbon double bond can create 2 possible structures. And again, that's because we do not have rotation around the carbon-carbon double bond. When we have an example here of 2-butene, so we have the double bond starting at 2 with 4 carbons total, we can have a cis isomer. This is when we have hydrogens on the same side as the double bond. Do you see the hydrogens here on the same side of the double bond? And trans is when we have hydrogen diagonal compared to the double bond, one on top and one on bottom. When we're talking about cis and trans, we're actually talking about the relative locations of hydrogens based on the carbon-carbon double bond. So these groups they have in pink, they're only the same right now because my example is 2-butene. It's not because they're the same that it's cis or trans. In fact, the R groups that come off of a cis and a trans, this R group and this R group, can be the same or different. My example, they happen to be the same. Each carbon must have a hydrogen for these isomers to occur. The alkyl groups can be same or different. All right, I have a bonus slide in here talking about drawing cis and trans isomers. So on the previous slide, I used 2-butene, and you saw that the R groups are the same as each other, CH3 and CH3. I wanted to show you that these are also cis and trans. First one is cis 4-methyl-2-pentene. If we take a look at this, I have 2 carbons, and my hydrogens are on the same side. My R groups are different, so this is a cis molecule. So what if I were to just give you this name and ask you to draw it? I would start off with pentene. I would do carbon, 2, 3, 4, 5. My double bond's coming off carbon number 2. Put my double bond in. I have a methyl coming off of 4, 1, 2, 3, 4. And then, if I needed the cis version of this, I would concentrate, let me change my pen color, I would concentrate on these 2 carbons here. This is where the cis and trans is going to happen. So I'm going to rewrite those 2 carbons with the 120-degree bond angle. And what I know is it wants me to draw a cis. Cis means the hydrogens will be on the same side of the double bond. So I'm going to go ahead and put those in right away on the same side as the double bond. All right, so now to finish the structure, I've already got the hydrogens handled for this carbon here. What's left over is this carbon here. That's on this carbon, so I need to put a CH3 here. And what's going on over on this side? I've got this whole piece here I have to add. Well, first thing is I'm going to draw this carbon bonded, then this carbon, and then this CH3. 1, 2, 3, 4, 5, 6. 6 carbons. 1, 2, 3, 4, 5, 6. Let's fill in the hydrogens. This one needs 3. This needs 1. That doesn't need any. And now I'm finished. That H is kind of hard to see. Sorry about that. All right. That's how you would draw it. So why don't you go ahead and practice drawing this one. I know I have the answer here. Let's go ahead and practice drawing this. Let me change my color again. I have a 2-pentene, 4-methyl-trans. Oh, that's very similar. So I have pentene, 1, 2, 3, 4, 5. Remember, these are my notes, my actual structures here. So on the exam, for example, I would circle this, and I would cross this out so no one looked at that. That would be the actual answer. These are my notes. So, okay, I have 2 pentene, 1, 2. That's my double bonds happening. Coming off of 4, 1, 2, 3, 4 is a methyl group. And I need a trans. So let's change the pen color again. It's these 2 carbons that are involved in cis and trans. That's where my double bond is. Let's go ahead and draw those at 120-degree bond angle. And because it's trans, let's put the hydrogens in right away. I could put the hydrogens on the left side or the right side. So let's go ahead and make it the same as the other one. I'll put a hydrogen here and a hydrogen here. Now what's left over is a CH3 on this carbon. Put a CH3 here. What's going on over here? Carbon, carbon, CH3. So let's count our carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, I didn't get too many. Finish it off with our hydrogens. This guy needs 3. This guy needs 1. And there we have it. We have our cis version versus our trans. This also illustrates how you draw them, the 120-degree bond angle. This would be my notes. This piece right here would be my answer. On the exam, don't leave notes like that. Go ahead and cross that out so I know this is the answer to make it nice and clear. These are just my notes. This also illustrates that the R groups can be different. It is the relative positions of hydrogens to the double bond that causes cis and trans isomers. I went ahead and cleaned that up because I want to show you another thing. Cis and trans can be shown as line structures. This is the same structure as the one right over here. Do you see the carbon-carbon double bond here? This is cis. When you have the double bond inside like this, where this bond's going down over here and down over here, this is showing cis. In a line structure to show trans, you would have the zigzag pattern, and you could see that if you were to fill in the hydrogens, my hydrogens on a line structure would be cis. I'd fill in my hydrogens here. They would be trans. You definitely want to practice how to do a line structure illustrating cis and trans. You cannot have cis or trans isomers in a terminal alkene. This is a picture that your textbook gave you. I don't like this picture. Why did they use the letter D? Why did they not just use hydrogens? So what they're telling you is if you have a terminal alkene, that means the double bonds on an N carbon, and these are both hydrogens, it's not cis or trans. Here's an example of where cis and trans doesn't exist. Notice my terminal carbon has 2 hydrogens on it. Another type of stereoisomer, which is also an isomer which different in 3-dimensional space, is when you have these kind of compounds here that are not cis and trans because we don't have the hydrogens relative to each other on the carbon-carbon double bond, but we clearly have the same compound, but they're different. Take a look at this first one here. It's labeled E, and I'll explain why it's E here. Notice on this carbon here we have a chlorine on the top with bromine on the bottom, where here we have a bromine on the top and chlorine on the bottom. There's no free rotation, so these are different molecules. They'll come up with the exact same name because this would be a 1-bromo, 1-chloro, propene. This would be a 1-chloro, 1-bromo, propene. They have the same name, but they're not the same structure. So they had to come up with a new designation that's called E and Z. How you do this is priority. We're going to go ahead and take these 2 relative to each other here. And whichever is directly bonded to the carbon, whichever one has the higher atomic number, it gets higher priority. So this carbon is higher in atomic number than a hydrogen. So this would be high. That's an H. Sorry, it doesn't look like an H. And this would be low. Higher atomic number, lower atomic number. Now let's compare chlorine and bromine. Well, if you take a look at the periodic table, chlorine comes before bromine, so this would be high, and this would be low. All right, so you compare them against each other. Now, where the E and Z comes in, do you notice looking across this way, going across this way at the double bond, I have a high with a low, and I have a high with a low. That means it's E. E, indigen, means it's opposite side. This would be an E. All right, let's do this one more time here. Carbon comes before hydrogen, so this would be high, this would be low. Bromine and chlorine, this one's high, and this one's low. So you can see over here, this is the same designation. Looking across this way, you have a high with a high, and you have a low with a low. That would be Z, zusammen. They're on the same side. So on this case, we would have E in front of its name, and on this case, I'd have Z in front of its name, just like we did cis and trans, and you'd put a dash after it. On the next slide, we'll go over priorities in a little more detail, and then we'll look at some naming. The system for comparison on priority. You need to rank atoms that are connected at the comparison point. In this case, that would be the carbon-carbon double bond. So directly attached here would be a carbon, directly attached here would be a hydrogen. The higher atomic number gets higher priority. So in this case, this guy's higher than this one. And this was our example from before. Bromine is higher than chlorine from atomic number. If there's a tie, then look at the second, third, etc. until a difference is found, until a tie is broken. Multiple bonds are equivalent to the same number of single bonds. What this means is if you have a carbon double bonded oxygen, this would count as 2 bonds to oxygen, 1, 2. So this would have priority over a carbon single bonded to oxygen. This would be a higher priority. Here's an example of how you'd use the name. A lot of times the letter E is put in parentheses and then you have a dash. So this one's the E. Z would be the same type of notation. You'd put the Z or the E in parentheses, then a dash. Sometimes they don't put the parentheses. Let's take a look at extended comparison. If the atomic numbers are the same, compare the next connection point at the same distance. Compare until something has an higher atomic number. Don't combine, just always compare. So what that means is, do you see that this guy here is the same as this here, just expanded, and the CH3 is expanded? So we're starting off here. And when I go one out, I have a tie, carbon and carbon. So then what I do is I go to the next, let me change the pink color here. I go to the next carbon attached. So this carbon here is my new attachment point. I have a hydrogen, and a carbon. So the highest comparing would be a carbon. On this one, I have a hydrogen, and a hydrogen. Nothing's higher than a carbon. This guy wins. This guy has higher priority. Now it's your turn to classify these as E or Z. First thing you want to do is go high and low on the left side and right side. Remember, relative to the double bond, if both highs are on the same side of the double bond, then you have, which one? You have Z. Go ahead and pause the video, come back and check your work. All right, let's take a look at this. I have carbon comparing to iodine. Iodine is higher. I have carbon with carbon, so we have a tie. Then I have oxygen, but this is 2 times oxygen because of the double bond. And this I have an oxygen, that's just 1 time oxygen. So this guy gets to be high because it's 2 times to oxygen comparing to only 1 time to oxygen. So I have highs on diagonal to each other. That would be an E. This one I have carbon tied. This one here has 1 carbon, 2 carbon. So this one has 2 times carbon. This guy here has a hydrogen. Well, I didn't even count the hydrogen up here. I found the carbon. This has a carbon and a hydrogen. This only has 1 time carbon. So this guy gets to be high. And chlorine and hydrogen, we can see that this is high. Highs are on the same side. That would be Z. All right, this one has a carbon. This has a carbon. We're tied. This time, instead of showing you the hydrogens explicitly, I wrote it as a condensed structure formula. So this one has no more bonds to carbon, while this one still has 1 more. That would be high. And I have chlorine versus carbon, so this is high. They're on the same side of the double bond. That would be Z. This one, we don't have a tie on this side. We have chlorine here, and we have oxygen, so chlorine would be high. This one, C, is actually triple bonded to nitrogen. That's what CN is. It's C triple bond N. So I have a tie on my first carbon here. This carbon has 1 bond to nitrogen, so 1 times nitrogen. But this one has 3 bonds to nitrogen, so that gets to be high. And they're on the same side. That gets to be a Z. How'd you do? So for this one, I want you to go ahead and name the following. I'm going to let you know they're both going to have E and Z or E or Z in front of the name. Go ahead and name them as though E and Z doesn't exist. And the last step, find the E or Z, put it in parentheses in the front of the whole thing. Right, this one, longest continuous chain regardless if it bends and twists, is right here. I have a 1,3-pentadiene. This would be carbon number 1 because that's where the double bond is the shortest distance. Comparing E and Z, I have a high down here and a low here. And on this side, I have a high here because it's double bonded to carbon. This one's only bonded to hydrogens when you get down to here. My highs are on opposite sides here. So what goes in front here? E. All right, longest continuous chain, which contains both of these double bonds, goes here. This actually is an isopropyl group. It's an isopropyl group here. And then comparing, I have a carbon here. Here's my carbon-carbon double bond. I have a carbon here. So those are tied right now. And then this has 2 bonds to carbon, 2 times carbon. This guy has 2 bonds to carbon, 2 times carbon. So since this guy has 2 bonds to carbon, and this has 2 bonds to carbon, how come this one's higher and this one's not? It's because I need to go one further out. This guy and this guy. I'm comparing these two now. This guy and this guy. Notice this guy is bonded to 1 carbon if you look backwards, and this is bonded to 2. So this is 2 times carbon, and this guy's only 1 times carbon. Kind of tricky, huh? So this becomes the high, and this becomes the low. Bromine is higher than hydrogen, so my hydrogens are my highs are diagonal from each other. So what goes in front? This is also an E. All right, so I wanted to clean that up so you can kind of see the highs and lows better, and maybe you can go ahead and try this on your own. I wanted to go ahead and end this with a basic guide to decoding organic compound names. It shows you organic compound representation, functional groups, bond types, parent chains, side chains, and stereoisomers. And we haven't gotten to this very last one here, R and S. That's going to happen later on in the semester, maybe even next semester. But you can see the cis and trans representation of the line structure. Looking at bond types here, I like how this shows you how a triple bond, this is actually 1, 2, 3, 4 carbons when we're talking about a line structure. And go ahead and take a look at this poster and see if it helps explain a few things.